In the 1950s, one factory changed American railroading forever. This is the story of how the EMD F7 locomotive was built. Welcome inside the legendary La Grange factory. The massive EMD plant stretched across 383 acres in McCook, Illinois. Every morning, thousands of workers arrived at the factory gates. Men in wool coats and flat caps carried their lunch pails to work. The security guard checked each worker's badge at the entrance. Inside the locker rooms, workers changed into their work clothes. Blue chambray shirts and heavy denim overalls were standard attire. Steel-toed leather boots protected their feet from falling metal. Workers punched their time cards at mechanical clock stations. The factory employed over 14,000 workers at its peak. 3 shifts kept the plant running around the clock. Long corridors connected the different divisions of the factory. Steam pipes ran along the ceilings wrapped in white insulation. The air was thick with welding smoke and the smell of hot metal. A natural light poured through massive industrial windows. This was the birthplace of diesel locomotives. Here, the future of American railroads was being forged. The main erecting hall was a cathedral of American industry. Ceilings soared over 30 feet high with steel beam trusses. Sawtooth skylights allowed natural light to illuminate the workspace. Railroad tracks were embedded directly into the concrete floor. Multiple F7 locomotives stood in various stages of construction. Massive 200-ton overhead bridge cranes spanned the entire hall. Crane operators climbed tall steel ladders to reach their cabs. From their elevated position, they could see the entire factory floor. The crane controls were simple brass levers and mechanical switches. Workers below looked like ants compared to the massive machines. Welding sparks flew constantly, illuminating the industrial darkness. The noise was relentless, hammering, grinding, and riveting. Communication happened through hand signals and shouted commands. A ceremonial bell rang each time a completed locomotive rolled out. At peak production, that bell rang 5 times every day. Every F7 began as raw steel in the materials storage yard. Massive steel plates were stacked on heavy wooden timbers. Each piece was marked with chalk indicating its destination. I-beams, channel sections, and angle iron filled the storage area. Overhead, cranes lifted the heavy steel using chain rigging. Workers used hemp rope tag lines to steady swinging loads. The steel was sourced from foundries across the Midwest. Quality inspectors checked each delivery for defects. Material handlers moved steel on small rail cars through the plant. The raw materials would be transformed into precision components. Steel plates weighed hundreds of pounds each. Proper material handling required years of experience. One wrong move could cause serious injury or death. Safety was important, but production quotas drove the pace. From here, the steel began its journey to becoming a locomotive. In the fabrication building, steel cutting began. Workers used oxy-acetylene torches to cut thick steel plates. The cutting torch produced a bright flame and shower of sparks. Acetylene and oxygen tanks stood on wheeled carts nearby. Rubber hoses connected the tanks to the brass torch assembly. Workers wore dark welding goggles and leather aprons. Heavy leather gauntlets protected their hands from burns. The cutting line followed chalk patterns marked on the steel. Smoke rose from each cut as metal melted away. Mechanical shearing machines cut thinner steel sheets. The massive shear had a cast iron frame weighing several tons. A large flywheel provided the power for each cut. The blade descended with tremendous force, shearing through steel. Cut pieces fell into collection bins below the machine. But press brakes bent steel plates into precise angles. Workers positioned each plate against the back gauge carefully. The operator controlled the ram with a foot pedal. Scale indicators showed the exact bending angle in degrees. Sheet metal rollers curved steel into cylindrical forms. 3 parallel rollers gripped and bent the steel gradually. Hand wheels adjusted the roller positions for different curves. These curved sections would form the locomotive's distinctive nose. Every cut and bend had to meet precise specifications. Quality control inspectors measured each piece with calipers. Rejected pieces were sent back to be recut or scrapped. The underframe was the foundation of every F7 locomotive. Heavy structural steel formed the main center sill. This beam would carry all the compression and tension loads. Cross members provided lateral rigidity to the frame. Bolsters at each end would connect to the wheel trucks. Workers positioned the steel members on large assembly jigs. The jigs held everything in precise alignment during welding. Arc welding joined the heavy structural components together. Welders wore black vulcanized fiber helmets with dark filter glass. The welding arc produced intense light that could blind unprotected eyes. Electrode rods were consumed rapidly during the welding process. Workers changed rods dozens of times during a single shift. The smell of burning flux filled the welding area. Completed welds were inspected for cracks and porosity. The bad welds were ground out and re-welded until perfect. The underframe took shape piece by piece. Multiple welders worked simultaneously on each assembly. Sparks showered in all directions as metal fused together. The finished underframe weighed several thousand pounds. Overhead, cranes lifted completed underframes to the next station. Workers guided the heavy load using rope tag lines. The underframe was placed on flanged wheel dollies. These dollies rode on tracks embedded in the factory floor. From here, the underframe would move through the assembly process. Each station added more components to the growing locomotive. The F7's car body was not just a shell, but a structural element. Side panels, roof, and underframe worked together as one unit. This semi-monocoque design provided exceptional strength. Sheet metal workers shaped the outer skin panels. Portholes, round windows, were cut into the side panels. Louvered air intake sections allowed engine ventilation. Access doors provided maintenance entry points. Internal structural bracework reinforced the car body. Workers climbed scaffolding to reach the upper sections. Spot welding joined lighter gauge skin panels to the frame. The distinctive bulldog nose was constructed from 4 steel sheets. Each nose section was pressed in large hydraulic presses. The compound curves required skilled metalworking techniques. A cylindrical headlight housing was integrated into the nose, and all sections were welded together with precision. Automotive bonding putty filled and faired the curved seams. This technique came directly from General Motors car divisions. The windshield design resembled late 1930s Buick automobiles. Even the window crank handles matched GM car parts. Workers sanded the putty smooth using hand blocks. Multiple coats of primer were applied to the bare metal. The car body slowly took its iconic streamlined shape. Rivet guns secured additional structural reinforcements. The pneumatic rivet guns produced a loud, staccato rhythm. Workers wore no hearing protection despite the intense noise. Completed car body sections were inspected before final assembly. Measurements verified the precise dimensions required. The bulldog nose gave the F7 its distinctive appearance. This design provided both style and safety for the crew. Railroad companies loved the modern streamlined look. The heart of every F7 was the EMD 567B diesel engine. This massive power plant produced 1,500 horsepower. 16 cylinders were arranged in a 45-degree V formation. Each cylinder displaced 567 cubic inches. The total engine displacement was over 9,000 cubic inches. Engine assembly took place in the dedicated engine division. Diesel engines sat on large carriages with flanged wheels. These carriages rode on parallel tracks in the factory floor. Workers pulled the carriages with winches as assembly progressed. The engine block was not a casting, but a welded steel structure. Steel channels formed the backbone of the crankcase. This innovative design allowed field repairs with standard tools. The crankshaft was the first component installed. Main bearing nuts were torqued to 800 foot-pounds. Workers used massive torque wrenches for this critical task. Cylinder liners were heat-treated cast iron with mirror finish bores. Double walls contained cooling water passages. Transverse ports allowed air intake for the two-stroke cycle. Pistons were pearlitic, malleable iron with special crown designs. The recessed combustion chamber improved fuel efficiency. Deeply ribbed undersides helped cool the pistons. Connecting rods linked each piston to the crankshaft. Precise torque values ensured reliable operation. Workers followed detailed assembly manuals for each step. The Roots-type supercharger was mounted at the engine rear. This blower forced air through the intake ports. Unlike turbochargers, it provided instant response. Overhead camshafts operated the exhaust valves. 4 poppet valves per cylinder handled exhaust gases. Mechanically controlled unit injectors delivered precise fuel amounts. These injectors were a patented General Motors design. The Woodward governor maintained consistent engine speed. All fuel system connections were carefully sealed and tested. Flywheel mounting bolts were torqued to 1,200 foot-pounds. The completed engine weighed over 20,000 pounds. At peak production, 11 engines were completed daily. Each engine cost over $32,000 to build. Completed engines moved to dedicated test cells. Water brake dynamometers measured horsepower output. Technicians verified oil pressure and operating temperatures. Fuel consumption was carefully measured and recorded. Governor response was tested at all throttle positions. The 8-notch throttle provided incremental power control. Only engines passing all tests moved to locomotive installation. A failed engine meant costly rework and production delays. The electrical systems transformed engine power into motion. The D12B main generator was the heart of the electrical system. This massive generator produced 600 volts DC. EMD manufactured all electrical components in-house. Armatures, bus bars, and housings were built on site. Copper wire was wound precisely on generator cores. Insulation testing verified the integrity of all windings. The generator was coupled directly to the engine flywheel. This created the unified engine generator power set. 4 D27C traction motors would drive the wheels. Each traction motor was built in the transmission division. Mega testing checked insulation resistance on every unit. Workers carefully assembled the motor housings and cores. Brush assemblies required precise adjustment. Completed motors were tested under load before installation. The D14 alternator provided power for cooling fans. This 3-phase unit produced 80 kilowatts. An auxiliary generator powered batteries and lighting. The Delco A8102 unit produced 74 volts DC. Wiring harnesses connected all electrical components. EMD used fasten connectors throughout the system. Miles of copper wire ran through each locomotive. Electricians followed detailed wiring diagrams. Every connection was carefully made and inspected. The main electrical cabinet housed control circuits. Contactors and relays controlled power distribution. Ground fault protection prevented electrical fires. Workers tested every circuit before final assembly. Electrical problems could strand a locomotive on the main line. Quality control was essential for reliable operation. The transition system allowed 4-step power control. The series parallel switching optimized tractive effort. Both automatic and manual modes were available. This system improved on the earlier F3 design. Railroad engineers appreciated the smoother power delivery. The wheel trucks carried the entire weight of the locomotive. Blomberg B trucks used cast steel frames from outside foundries. General Steel Castings supplied many of these heavy components. Each 2-axle truck received 2 traction motors. Coil spring primary suspension cushioned the ride. Leaf spring secondary suspension provided additional comfort. Swing hangers allowed lateral movement on curves. Workers assembled trucks on dedicated workstations. Heavy jacks positioned the truck frames for motor installation. Traction motors were nose suspended into each truck frame. Gearing connected each motor to its wheel axle. Different gear ratios suited different railroad needs. Freight service used higher ratios for pulling power. Passenger service used lower ratios for higher speeds. Wheels came from specialized third-party suppliers. Each 40-inch wheel was precisely machined. Clasp brakes with 2 shoes per wheel provided stopping power. Brake rigging connected to the air brake system. Workers adjusted brake shoe clearances carefully. Proper braking was essential for safe operation. Completed trucks weighed tens of thousands of pounds. Overhead cranes moved finished trucks to the assembly floor. The trucks waited on the tracks for the body drop. This moment would marry body to running gear. It was the most dramatic operation in the factory. The body drop was the climax of locomotive assembly. Completed car bodies hung from the massive overhead crane. The 200-ton crane slowly lifted the body. Workers guided the load using long hemp rope tag lines. The crane operator watched signals from the floor crew. Hand signals communicated precise movements. The body weighed approximately 100,000 pounds. Slowly, it was positioned over the waiting trucks. Center pins had to align perfectly with truck bolsters. Millimeters of misalignment could cause serious problems. The crane lowered the body with extreme precision. Workers called out adjustments as the gap closed. Finally, body and trucks became one machine. Securing bolts locked everything in place. The locomotive now stood on its own wheels. For the first time, it resembled a finished product. But much work remained before it could run. Electrical connections between body and trucks were next. Traction motor cables were routed and connected. The locomotive was taking its final form. The engineer's cab was the command center of the locomotive. Control stands were installed with precision alignment. The throttle lever had 8 running positions plus idle. Each notch increased engine speed by 75 RPM. The brake valve controlled the entire train's braking. The DSE-24H valve had 6 positions for different functions. An independent brake valve controlled locomotive brakes only. The reverser lever selected forward or reverse direction. Instrument gauges monitored all vital systems. Ammeter and voltmeter showed electrical system status. Water temperature and oil pressure gauges tracked engine health. Air brake pressure gauges showed reservoir levels. A speedometer displayed the locomotive's velocity. The cab had 2 seats for engineer and fireman. Large windows provided excellent forward visibility. The windshield wipers operated from air pressure. A horn valve controlled the distinctive diesel horn. The cab was surprisingly comfortable for its era. Heating came from the engine's cooling system. Railroad engineers appreciated the modern design. The air brake system was critical for safe operation. Westinghouse 24RL equipment was standard on the F7. A Gardner Denver compressor supplied compressed air. This 3-cylinder unit was driven from the generator shaft. Main reservoirs stored air at high pressure. Pipes connected the locomotive to every car in the train. Workers installed all brake piping with careful attention. Connections had to be perfectly sealed to prevent leaks. Air leaks could cause brake failures on the main line. The automatic brake applied if air pressure dropped. This fail-safe design prevented runaway trains. Workers tested the entire system under pressure. Gauges verified proper operation at all positions. Only perfect systems passed inspection. Lives depended on reliable braking performance. The paint shop transformed bare metal into railroad art. EMD maintained an in-house styling department. Up to 14 artists worked on locomotive color schemes. Harry Urban Bokowitz was a legendary EMD artist. He painted over 100 different railroad schemes. Artists first created foundation drawings of each locomotive. Then they painted alternative striping plans called quickies. Railroad companies chose their preferred designs. Each scheme had to be distinctive and visible. Grade crossing safety influenced many design choices. Approved designs became official styling diagrams. These drawings specified exact DuPont color numbers. Stripe dimensions and placement were precisely documented. Surface preparation began with sandblasting to bare metal. Workers wore supplied air helmets during sandblasting. The abrasive removed all mill scale and contamination. Bare metal had to be primed within 1 hour. Red oxide or grey alkyd primer provided the foundation. Primer was applied using pressure-feed spray guns. DeVilbiss and Binks spray equipment was standard. The paint booth had continuous airflow ventilation. Air moved front to rear to control overspray. DuPont Duco lacquer was used on the carbody. This nitrocellulose lacquer dried in 30 minutes. Multiple thin coats built up depth and coverage. DuPont Dulux enamel-covered trucks and underframes. This tougher coating resisted chips and stone damage. Masking for multicolor schemes was extremely labor-intensive. Physical metal templates helped lay out complex curves. The nose alone could require 2 hours of masking. Each color was applied and dried before the next. Complex schemes required many separate masking sessions. The Santa Fe war bonnet was among the most famous. Red, yellow, silver, and black created the iconic look. Workers took pride in the beautiful finished products. After painting, the locomotive gleamed under the lights. Final detailing included lettering and number boards. Railroad heralds were applied with precision. The paint shop completed the locomotive's transformation from raw steel to rolling artwork in just weeks. Final assembly brought all systems together. Fuel tanks were mounted beneath the underframe. The 1,200-gallon tank provided long range. Lubricating oil and cooling water tanks were filled. All fluid connections were tested for leaks. Workers connected the steam generator for passenger service. The vapor Clarkson unit produced 1,200 pounds per hour. Water tanks for the steam generator were installed. Handrails and grab irons were attached to the carbody. Steps and platforms provided safe access. Bell and horn were mounted and connected. Headlights and marker lights were installed. All lighting circuits were tested for proper operation. Number boards displayed the locomotive's identification. The locomotive was nearly ready for testing. Fuel was loaded for the first engine start. The workers gathered to witness the moment of truth. The starter motor cranked the massive diesel engine. With a roar, the 567B came to life. Exhaust smoke billowed from the rooftop stacks. The engine settled into a steady idle. Technicians monitored all gauges and indicators. Oil pressure and temperatures were verified. The throttle was advanced through all 8 notches. The engine responded smoothly at each position. Load bank testing verified full power output. Resistor banks simulated traction motor loads. The entire electrical system was proven under load. Air brake tests verified proper operation. Compressor output and valve response were checked. The locomotive moved under its own power for testing. Track tests verified traction and braking performance. Railroad inspectors witnessed the final tests. Their signatures approved the locomotive for delivery. Another F7 was ready to join the American railroad fleet. Completed locomotives departed via railroad interchange. The Indiana Harbor Belt carried them to their new owners. Railroad representatives came to La Grange for acceptance. Formal handover ceremonies marked each delivery. Between 1949 and 1953, EMD built 3,849 F7 units. At peak, 5 locomotives were completed every single day. Over 50 railroads operated the iconic F7. Southern Pacific had the largest fleet with 530 units. Santa Fe operated 472 F7 locomotives. The F7 was priced at approximately $160,000 per unit. This was a bargain compared to operating steam power. Diesel required far less maintenance than steam. One diesel could do the work of multiple steam engines. The F7 helped kill the steam locomotive in America. By the late 1950s, most major railroads had dieselized. EMD captured 73% of the market. The La Grange factory became legendary in railroad history. The F7 was called the most famous face in railroading. Its bulldog nose became an American industrial icon. The factory that built them changed transportation forever. Today, few original F7 locomotives survive. Museums preserve these mechanical masterpieces. Railroad enthusiasts maintain operating examples. The sound of a 567 diesel still thrills crowds. The distinctive horn echoes across the countryside. The La Grange factory eventually closed in 1991, but its legacy lives on in railroad history. 14,000 workers built these machines. They were craftsmen who took pride in their work. Each locomotive represented countless hours of labor. The F7 represented the peak of American manufacturing. It was built with skill, precision, and pride. This was how the EMD F7 was built, from raw steel to railroad legend. Inside the 1950s EMD F7 factory,